In this installment, we're going to look at the eccentricity of ellipses in a little more detail. There is a formula that relates to the shape of ellipses and how they compare to circles. And that term is eccentricity. Eccentric means to be deviant or odd, not necessarily in a pejorative way, but to be different or deviate. So eccentricity is a measure of how much an ellipse varies from being a circle. So if something were a circle, its eccentricity should be a zero. So a circle should have eccentricity equal to 0. So the tool we've come up with for that is the ratio of the distance between the foci and the length of the major axis. So what I'd like us to do is take a look at 3 different ellipses and see what we get in looking at these different shapes. So if we start out with this top one, the circle that I've overlain on top, we can set about measuring it. And so I put this little grid on top so we could measure it. So the distance between the foci, well, wait a minute, the distance between the foci, if we started out with an ellipse like the one on the bottom, and we squashed it from the sides, pressed inward like this, it would become rounder and rounder still. And what happens in that case, in that process, is the foci get closer and closer together. So the distance between the foci in this case is 0. And there is a length of the major axis, and it's equal to the diameter. So 0 over the diameter, no matter how large it is, will be equal to 0. Thought we could put in a number 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0 over 9 is 0. And as we said, the eccentricity of a circle should be 0. And applying that formula in this case, we get 0. Now looking at our second case, we want the distance between the foci. Now it probably stands to reason to you that if we look at this distance, this total thing, which is the D, and we measure just from the center to the focus, that this distance from the focus is like the semi-distance to the focus, 1/2 the distance between the foci. And if we look at the length of the major axis, which is all the way from one side to the other, the distance from the center to either of those edges is 1/2. So if I take 1/2 the distance and 1/2 the length, I will still get the same ratio. In other words, if I have 8 over 16, and instead of measuring the 8, I had measured the 4, and instead of measuring the 16, I'd measured 8, both of those are 1/2. So we can measure just from the center to the focus. So in this case, we have a distance of 1, 2, 3, 4, 5. Maybe that's 5.5. 5.5. And this is 6, 7, 8, 9, and maybe 9.5. So we get an eccentricity using our calculator. 5.5 divided by 9.5 is 0.5789. Since we have 2 significant digits in our numbers, we can only report 2, so 0.58. Now, since these have the same units, say centimeters or blocks or dashes, whatever they are, they cancel, and an eccentricity, since it's a ratio, has no units on it. So we have 0.58. So it is more eccentric for sure than a circle. Now we should expect that this last one deviates from being a circle even more, so the eccentricity should be greater. And let's collect some measurements. So we have 1, 2, 3, 4, 5, 6, 7, 8. Let's call that 8 3/4. 8.75 all over the total axis, which is 9, maybe 9.5. 8.75 divided by 9.5. Gives us 0.921. We have two significant digits, so we have 0.92 is the eccentricity. So that's how we would compute the eccentricities of orbits. Now, what I included here is a table to show eccentricities of the planets in their orbits. And we can look at Earth, for example, is 0.016. It's a pretty low number. And in fact, they're all 0.0 something. They're less than a tenth, except for Pluto and Mercury, which have the most eccentric orbits in the group. Now, Mercury is unique because it's so close to the sun. It's so very, very close to the sun. That's what sets it off. So there's something about being very, very close to the sun that lends to it having a very eccentric orbit. And our next one is Pluto, which we know isn't even considered a planet anymore. And this fact, among others, so the eccentricity, among other factors, sets Pluto apart. And there's even more important why it's no longer considered a planet. It's a dwarf planet. So that's just looking at numbers here. So when we look at the rest of them, where does the Earth fall? We find that Venus is way smaller than Earth, but Mars is about 7 times more eccentric. Jupiter about 3 times, about 4 times for Saturn, about 3 times for Uranus. Way less eccentric is Neptune, way out there. Now let's compare that to the numbers we came up with for our objects, our ellipses. So the smallest of the 3 that we had, after 0, of course, is this 0.57. 0.57. 0.57 is more than twice the eccentricity of Pluto. So even Pluto, having the most eccentric over the orbits in this table, it's far closer to being a circle than our case number 2. Far closer to being a circle. And when we look at Venus, for example, its orbit would look very much like number 1. We could not detect anything that deviates from the circle at this scale. We need to be much more precise. And the Earth goes the same way. In fact, the Earth's orbit is so close to being a perfect ellipse, a perfect circle, and in this picture, it's drawn deviantly. Both the foci reside inside the sun. So this picture we had on the first page is very much an exaggeration. And if we come back to this one here, if the sun were at the blue, and we were to put the foci of the orbit in here, they would both be inside the sun. That's how close the Earth's orbit is to being a perfect sphere, or circle, and Venus is even better than that in terms of being a perfect circle. And so that's just a little bit more on eccentricity, how to calculate it. In our next installment, we will continue to look at Kepler's laws.